Hello and welcome to Unit 4.1 Polynomial Functions. So today our goal is to look at polynomials. So there's a bunch of different types where we're going to be finding x-intercepts, y-intercepts, and we're going to be doing rough sketches of them. So first I want to start with some very straightforward functions we've seen before, a linear function and a quadratic function. I'd like you to take a moment and try these problems on your own. If you can, pause the video to see how you are working. So hopefully you did actually pause the video because we're going to start by graphing a linear function. And so that's where we would start our y-intercept at 6, and our slope is -1/4. So we're going to go down 1, right 4, down 1, right 4, and then we can go back to our y-intercept. We can go the opposite way, meaning we can go up 1 and back 4. And then we can connect those points to the best of our ability, if we don't have a straight edge, with arrows on both sides. So there's our linear function. Our next one is a quadratic. And so this is where our vertex would be at 4, -7. Remember, same opposite. Then because of that a value, we're going to take our perfect squares. So x, y, 1, 1, 2, 4. And we're going to multiply those y values by that a value. So, oopsies. Whoa. I'm just going to fix that up a little bit. So, x and y, we're going to take those y values, multiply by 2. So we get 1, 2, 2, 8. So from our vertex, we're going to go over 1, up 2, reflect it over our vertex. And then we're going to go back to our vertex, over 2, up 8, and reflect it over our vertex. We're doing that again because of our axis of symmetry that goes through our vertex. And so we're going to connect our points to get our graph. So that was just a little review for our warm-up. Next, what we're going to do is we have a lot of definitions. Some of it is review. As you can see, what we're going to do is also have examples, just so that way we can take these definitions and kind of put it into something we can see a little bit easier. So a power function, it is a function of the form f of x equals ax to the nth power, where a and n are non-zero real numbers. So an example would be f of x equals 5x to the 4th power. Okay? Now, a leading coefficient, it is the coefficient of the first term when the polynomial is in standard form. So we can take the problem from our the example from our previous problem. Our lead coefficient is 5. That's our lead coefficient. I'm going to use LC for it. Now our degree, this is the value of the exponent in a power function. So in this case, our degree is 4. And we're all just kind of working off of that same original problem. Now a monomial function, this is a function of the form f of x equals ax to the nth power, for which a is a non-zero real number and n is a positive integer. So we can have f of x equals -2. That's perfectly fine. X2 squared. That is a monomial. It's one term. A polynomial is a monomial in one variable, is a monomial or the sum of 2 or more monomials. What it means is we can get 5x squared, that's a monomial, or 7x cubed plus 8x cubed. They have the same variable, same exponent, and we would get 15x cubed, another monomial. Standard form of a polynomial. A polynomial that is written with the terms in order from greatest degree to least degree. So an example that we might be given is a problem that has like 9x plus 7x squared minus 4x to the fourth power. We would rewrite it with our biggest degree first, so negative 4x to the fourth power plus 7x squared plus 9x as the standard form of that polynomial. Now a degree of a polynomial, very similar to degree up there, they're just more specific, is the greatest degree of any term in the polynomial. So for example, our degree for that polynomial would be 4 because it's our greatest exponent. Quartic function, this is a fourth degree function. So we have linear, we have quadratic, we have cubic. Now we have quartic, so that's where it's our parent function would be y equals x to the fourth power. And then a quintic, you might I'm hoping I'm saying that right, is the fifth degree function. And so our parent function would be y equals x to the fifth power. Okay, so what we're going to do now is we're going to go on to the next page. It still falls into this like definition area. It's just talking about like the difference between a polynomial and a not polynomials. So the big thing with a polynomial is that all exponents have to be positive integers. So like if you had positive 1/2, it wouldn't work because a half is not an integer. Integers are your counting numbers. You should really think of it more like your natural numbers. Natural or your whole numbers. Okay, so what we're going to do below is we're going to identify whether it is or is not a polynomial, and then if it is, we're going to write it in standard form, identify the degree and leading coefficient. So this is a polynomial because all of our exponents are positive. And so when we rewrite it in standard form, it would be negative 8x cubed plus 7x squared minus 6x plus 1. Now that it's in standard form, we can see that our degree is 3 and our leading coefficient is negative 8. So that's how we're getting those pieces. They all come from that standard form. That's a big place where people make mistakes, is forgetting to rewrite it in standard form. Now our next one is also a polynomial. The reason we can tell it is looking at our exponents. Are they all positive whole numbers? From here, we're going to rewrite it in standard form, so that's in descending order of our exponents. So positive 10x, to the fifth power, plus 7x cubed, plus 6x squared, and then minus 3x. And so our degree is 5, and our leading coefficient is 10. Again, this is where we're getting these answers. Okay, our last problem. So this is not a polynomial because this right here, if we rewrote it as an exponent, as a fractional exponent, would be x to the 1/2. It is not a positive integer or a positive whole number. And so that is not a polynomial, so we can't do anything else. For example, to these next 3 problems, I would really suggest pausing the video and trying these problems on your own just to test your skill. Hopefully you did actually pause the video. This is not a polynomial because of that x to the negative first power, so we can't continue on. Your next one, it is a polynomial because we have all positives. So we would end up with 7x to the fourth power plus 8x minus 2. So our degree is 4 and our lead coefficient is 7. And then finally, yes, it is a polynomial. And so when we rewrite it, be careful to not lose track. So negative 4x to the 7th plus 8x cubed minus 10x. Whoa, there we go. And so our degree is 7 and our lead coefficient is negative 4. It is possible that your lead coefficient is negative, but your degree will always be positive. So what we're going to do now is we're going to be looking for zeros and y-intercepts. And remember, zeros are also known as solutions or x-intercepts or roots. It's where the graph touches or passes through the x-axis. It's easier to find these in factored form. So what we're going to do is we're going to start with the fact that most of these are going to be already in factored form or given a graph. So our x-intercepts, how we find them is we take our factors, set them equal to 0, and solve. We saw this in Unit 3, so hopefully this is review, but we're going to isolate our variable, and so what we get is x equals -2 and x equals +1. So those are two x-intercepts. Now to find our y-intercept, what we're going to do is we're going to replace all the x's with 0 and simplify. Now I would suggest having your calculator out for this, unless you want to do it in your head, which is perfectly fine, or by hand. So y equals 4 times 0 plus 2 times 0 minus 1. So what we get is y equals 4 times 2 times -1, which is y equals 8. So our y-intercept would be at 8. Okay, next page. So example 4 is looking at a graph. What's nice about this is all we have to do is identify where our graph hits the x-axis and the y-axis. So our x-intercepts are going to be at -2, 1, and 3. So x equals -2, 1, and 3. And our y-intercept is where it passes the y-axis, which is at 2. So y equals 2. Okay, example 5 is a little bit more a little different. However, we've talked about it before. Because of that variable in the front, we're going to set 0 equals to -4x. Dividing both sides by -4, we get 0 equals x. And then if we want, we can do even more work. X minus 2 equals 0, and x plus 3 equals 0. Solve for x. And so x equals 0, 2, and -3. We have 3 solutions. Now, if we plug in 0, we would get y equals -4 times 0 times 0 minus 2. You might start seeing a shortcut. Times 0 plus 3. We would get y equals -4 times 0 times -2 times 3. Well, one shortcut is we can see that this 0, well, anything times 0 is 0, so our y-intercept is going to be 0. Now, if you have a solution at 0, your y-intercept will most likely also be 0. Okay. Example number 6 is a little bit more challenging because it's not in factored form. So what we're going to do is we're going to start by factoring out a GCF because they all have 5 in common and they all have x squared in common. What that leaves us with is x squared minus 5x plus 4. We can then work with the inside piece to factor it. So I'm going to do some space on the side. So 8 times c is 4, b is -5, so our two numbers are -4 and -1. So y equals 5x squared times x minus 4 times x minus 1. So there's our factored answer. Now, I want to show some real quick work with that 5x squared equals 0. So if we divide both sides by 5, because we first want to isolate that x squared term, we would get x squared equals 0. Well, when we square root both sides, we get, technically, x equals plus or minus 0. Now, we usually just write it as 0. The reason I want to show that work is it's going to make more sense in our later notes, that plus minus 0 while I talked about it. But anyways, we can still see the other answers. X equals +4 and +1. There's the rest of our answers. And then our y-intercept, if we plug in 0, well, we would get y equals 5 times 0, because 0 to the 4th power is 0, minus 25 times 0 cubed, which is 0, plus 20 times 0 squared, which is 0. So anything times 0 is 0. So 0 minus 0 plus 0 is 0. And we can also see it right there. Okay. I would suggest maybe stopping the video and trying 7 and 8 on your own. If not, what we can do is you can keep going, but otherwise, pause the video. Okay, hopefully you paused it, and you are checking your answers now. So x would equal -1, 3, and -4. And our y-intercept, the shortcut, if you start to see it, is you just multiply all the numbers that are showing up. So -2 times 1 times -3 times 4 would give us y equals +24. Our next one, x equals 0 and +3. And so because of that 0, what happens is we have 0 times -3. Anything times 0 is 0. Now our last one, we have, if we want to think about expanding it, y equals 2x times x plus 4 times x plus 4, because that's what that squared terms means. So our answers would be 0, -4, and -4. Well, we usually don't say that we have multiple solutions, so we just say 0 equals -0 and -4 for our x-intercepts. This right here is going to come up in a future lesson, kind of like what we saw up above in example 6. But anyways, for example 9, we have x equals 0, so then we can kind of assume that y is also going to be 0, because if we plug it in for that x by itself, it makes everything 0. Okay, so our next page, I know it's a long video, but you can do it, I believe in you, is a degree of a polynomial. So in standard form, it's your highest exponent. So our highest exponent is 2, so our degree is 2. Factored form, where we add up all the variable factors. So like this is 2 plus 1 plus 2 is 5, and so our degree is 5. What the degree tells you is how many solutions you'll have. So like y equals 4x squared minus 5x plus 7, we would have 2 solutions. Our next one, factored form, that x squared, we would have 2 solutions there, 1 solution at x minus 3, 2 solutions with x squared plus 4. So end behavior of a polynomial. So the reason that we wanted to find those degree is based on the degree, it tells us the shape of your graph. So if you have an odd degree, think like y equals x or y equals -x, it's going to look pretty linear. Now, if you have an even degree, so y equals x squared, or y equals -x squared, or even, like y equals x to the 4th power, we're going to have a U shape. And so like for odd degree, even y equals x cubed is going to look kind of linear. The reason that it's linear, and that's going to kind of help us with our end behavior, is if it's odd as x approaches -infinity, well, I guess it depends on your reflection. It'll either be -infinity or in positive infinity, and then as x approaches positive infinity, it's going to be negative or positive. So the reason I wanted to talk about that is if it's an even degree, like right here, and our lead coefficient is positive, we're gonna have positive infinities. Now, if it's an odd degree and it's positive, it's going to be going in opposite directions. And so like sometimes I think opposite for odd. So that's an example of x to the 5th power. They'll be having -infinity and positive infinity. Likewise, if you have a negative coefficient for an even, they're going to be both negative, and then an odd with a negative, it's just going to flip it, giving us that graph, and so our end behaviors are also going to flip. It's a lot going on, a lot to process. Let's just go to example 10, and we'll do this one, a couple of these together. So for example 10, what you're going to do is you first are going to just state the degree. So it is 4, that's your exponent, and so that means it is an even graph. Now our lead coefficient is 3. It is a positive graph, or a positive number, and so what that means is we're going to have a happy face because we're working with an even and a positive coefficient. So our end behavior is that as x approaches -infinity, f of x is going to approach infinity on both sides. Our next problem, Our degree is 3, which is odd. Our lead coefficient is -6, so it's negative. What it means is it's going to be going down. And what I like to have it more is it's going to look like this. It will have a little bit of a curve because it's not a perfectly linear function. And so we're going to be positive infinity on the left, negative infinity on the right. And you can kind of see that by having that shape image to kind of help see that end behavior. Our next problem that we're going to do together, our degree is 6, so that's even. You don't have to write even. I just do it because to kind of bring attention to it. -1, so that's sad face, because it's even. And so we're going to be going towards negative infinity of our y values on both sides. Okay, hopefully you kind of get it. I would suggest pausing the video and trying example 11 on your own. Hopefully you did. Oh, these are a little challenging. And so what we're going to do is our degree is going to be adding up our exponents, so 1 plus 1 plus 1. So our degree is 3. Our lead coefficient is 4, which is positive, and so our shape is going to look like this because it doesn't reflect. Oopsies. And so we're going to be, as x approaches negative infinity, as x approaches positive infinity, positive infinity. Okay, our next one, we have 2 plus 1, which is 5. Our lead coefficient is -1, so it's going to flip that graph. And so we're going to flip those end behaviors because both of our degrees were odd, and so that's our shape. Our last one is 1 plus 1 plus 1 plus 3, which is 6, so that's a positive. Our lead coefficient is, positive, 3. And so our graph, because we're working with even, it's going to be like this, like a U. And so we're going to be going to infinity on both sides. That shape is going to help us in our next couple lessons where we start to kind of graph the shape. Our last thing that we're going to do on this page is we are going to be stating the number of real zeros and the end behavior. So a real zero, how many times it passes the x-axis. So we pass the x-axis 3 times, which makes sense because it's like, voila, which is an odd degree. And so then we would be going to negative infinity and positive infinity. And since we didn't flip it, a is positive. Now we don't know exactly what it is, but it's just kind of like reiterating where we can get a positive from. Our next graph, we pass it once, twice, 3, 4 times. Whoa. So it's an even number, which supports the fact that it's U-shape. And so we're going to be positive infinity, which a must also be positive because we're happy. Positive. It's a smiley face. And then finally, we're going to go into the last page. I would suggest maybe trying example 12s. Got to fix that in the future. Example 13 on your own. Hopefully you did. And so we have 4 real zeros, and it is a U shape, which supports the fact that if we have an even exponent, it's going to be U shape. And so positive infinity, a is going to be also positive. And then our last one, we hit the x-axis 3 times. So because it's odd, does it support the fact that we have a kind of like a slanted shape? Yes. And so we're going to be going to negative infinity on the left, positive infinity on the right, and our graph is still going up. So a must be positive. Okay, so that is the end of 4.1. Hopefully you can see lead coefficients, graphs, degrees, all of that, but come with your questions so we can go over them in class. I would suggest filling out the summary and things to remember in your notes, and I will see you in class.